Hello. In this short video, I would like to discuss a small insight into ordinary differential equations, which I believe helps you to get a better grasp of the theory. In fact, to explain this best, I would like to take a small diversion into the field of philosophy. Namely, a few hundred years ago, during the European Age of Enlightenment, there were many philosophers around who were philosophizing around how does the world work, what constitutes the basic laws of the world. And around 1700, Isaac Newton had published his works on classical mechanics and celestial mechanics, including gravitation. So many smart people were around back then. And back then they had this idea about the world as what we now call a clockwork universe. Now, the idea of the clockwork universe is the following. If you have an old mechanical clock, if you set it to a specific time and then let the engine run, then the clock will run completely mechanically, just like it was designed. And you don't need to interfere with it anymore. The entire behavior of the clock is determined by the initial state and then by the mechanics on how far the clockwork is going to evolve. And that's all you need. And when I think of initial value problems, and I think of ordinary differential equations with an initial value, then I think this clockwork metaphors is actually the best you can find for this. And I like to think about ordinary differential equations with an initial value as something similar as this clockwork universe. You set the initial value, and then the evolution of the system is completely determined only by the differential equation. Getting back to this clockwork metaphor, let's suppose I stop the clockwork at some point. So it has been running and I stop it, and the clock shows a certain time. Now, if I switch on the clockwork again, it's just going to run smoothly, just as before. And something similar can also be said differential equations with an initial value. Let us take a look at a short example. Suppose I've got the following differential equation. Y prime of t is equal 2 times y of t plus exponential of 3 times t. And the initial condition at t equals 0 is y0 equals 6. So I like to think about it as follows. I set the variable y equals 6 at the starting time 0, and then I let the variable y evolve according to this differential equation. Just fix the initial condition, then you push the start button, and y evolves according to that differential equation. Now, if you take a look at this differential equation, then we recognize that it has a form for which we have found an explicit formula in a previous video. If I write down this explicit solution formula, I get the following, namely y of t is equal exponential of 2 times t multiplied with the integral from 0 to t of exponential 3 times u times exponential of minus 2 times u du. And then we have got the term corresponding to the constant of integration, namely plus 6 times exponential of 2 times t. Now, fortunately, the integral here can be computed exactly without much effort. Namely, I simplify this to exponential of 2 times t takes the integral from 0 to t of exponential u du, plus again 6 times exponential of 2 times t. And as I compute the integral, I get the following, namely exponential of 2 times t multiplied with exponential of t minus 1 plus 6 times exponential 2 times t. And if I simplify this even further, what I get is exponential of 3 times t minus exponential of 2 times t plus 6 times exponential of 2 times t. Okay, that is the formula for the solution of this differential equation with that initial value. And at this point, I suggest that you explicitly check that this formula here indeed defines a solution of that differential equation with that initial value. As I already said, you can fix the initial value at t equals 0, and then we let the system evolve according to that differential equation. Let's suppose that I let the system evolve. Okay, and then as t grows, the variable y evolves, and at some point I push the pause button, and the system freezes. So, for example, at t equal 1, I stop the system from evolving, and I get, okay, y at t equal 1 is the same as exponential of 3 minus exponential of 2 plus 6 times exponential of 2, which can be simplified to exponential of 3 plus 5 times exponential of 2. Okay, I only know this value at t equal 1. If I then push the play button again, the system will evolve just as before. And the way I interpret it is as follows, namely, the solution to y prime of x equal 2 times y of x plus exponential of 3 times x with initial condition y naught equals 6 is the same as the solution to the following, namely y prime of x equal 2 times y of x, the same differential equation, but this time I can fix the value at t equal 1 to be exponential of 3 plus 5 times exponential of 2. So instead of fixing an initial value, I can characterize the solution simply by fixing the value of the solution at any point in time. In fact, when we discuss the numerical solution of differential equations, we will repeatedly play and freeze the differential equation with different starting values at different points in time.